Mr. Moore's math class!
Good afternoon, guys, and welcome to Mr. Moore's online flipped classroom. Now, guys, we've got plenty to get through today because we're going to learn all about how to convert normal quadratic functions, that is something that looks like this, that is y equals ax squared plus bx plus c, into something that looks like this. Now we're also going to learn how to sketch these functions because it's a slightly different method that we would normally use, especially when it comes to the turning point. Now we're also going to learn all about the different transformations, dilations, and translations and all that type of thing that occurs when we change our a, b, and c values. So let's not wait any longer and let's get stuck straight into the lesson. Mr. Moore, you right down there? Sorry about that one. Anyway, guys, before we go too far into the lesson, it's really important that we learn all about some of the key words or terminology that you're going to come across when working with quadratic functions in the power form. So let's check out a little animation that I made the other day in order to be able to do this. Check it out.
Now today we're having a look at quadratic functions in turning point form. Now if we remember back to what we learnt whilst working with linear functions, a graph is essentially just a picture that represents a pattern, and this can also be seen in the case of a quadratic function, where y basically is the how high rule. That is, how high is the line for any given value of x, or how far does each x coordinate need to move in order to be on the line and follow the pattern, that is. Now whilst we've had a look at quadratic functions that have been written in the form y equals ax squared plus bx plus c, they can also be written in the following form, that is the power function form, or in other words the turning point form, where y is equal to a bracket x minus b squared plus c. We call this a general equation for a quadratic in this form, where a, b and c will affect the shape and location of your basic graph of y equals x squared in a number of ways. So before we delve too far into this, let's have a look at the basic graph of y equals x squared, shall we? Now as you can see, every coordinate along the x-axis has actually been squared to tell us how far up along the y-axis the line is. And of course we join these dots with a line to represent all of the millions of dots along the x-axis that are in between that we can't actually see. Now as I explained before, for the general equation that you can see above, your a, your b and your c values, that is the ones that are listed in red, will actually affect the shape and location of this normal quadratic equation, that is a y equals x squared graph. So let's have a look at the effect of a first. So as you can see, I've substituted in an a value of 2 and left b and c as 0. Now when I simplify this, the zeros will have no effect, leaving me with the equation y equals 2x squared. So what this means is every coordinate along the x-axis is multiplied by 2 after it's been squared. So this actually has the effect that you can see on the screen now. And of course we draw a line to represent the millions of dots that I hadn't previously included. Now as you can see from the arrows, each y coordinate along the red line is twice the height of the y coordinate along the blue line. Now this is because everything has been multiplied by 2, and we call this a dilation by a factor of 2 from the x-axis. Now what if our a value is something like 1/2? Well, I substitute 1/2 for a and 0 for b and c, and this ends up leaving me with y equals 1/2 x squared. Now what you can see here is all of the dots have gone half the distance from the x-axis because we've actually halved every value that we've got. Now this is once again highlighted by the distance that the arrows have to travel in order to reach each line. As you can see for the blue line, they actually need to go twice the distance of the red line, therefore the red line is half that of the blue line. And in this case we say the red line has been dilated by a factor of 1/2 from the x-axis. This is because the a value is equal to 1/2. So now it's time to explore what will occur if I make my a value negative. Now you can see this here in the equation y equals -1 times x minus 0 squared plus 0, and this simplifies to get us y equals -x squared. Now watching the dots of the y equals x squared graph, you can see that they've all moved down to below the x-axis. And this is because after we square each x coordinate, we put a negative out the front. This makes all of our answers negative. So if you can imagine for a second that the dotted line along the x-axis is a mirror, what you can see is the red line is an exact reflection of the blue line. That is, -x squared is a reflection of x squared. So summing up, if we get a negative a value, we essentially get a reflection in the x-axis. So here's a question for you. What will happen if our a value is -2? Well, we'd substitute in -2 for our a value, leaving our b and c value 0. That will get us y equals -2x squared. Now as you can see, the negative will cause a reflection in the x-axis, and the fact that there's a 2 out the front will result in each of the coordinates being multiplied by 2, stretching the graph further away from the x-axis. So once again, using the mirror analogy, you can see that the graph has been reflected in the x-axis and then has been dilated by a factor of 2 from the x-axis because it's had to go twice the distance. So when asked to comment on any transformations that have occurred, you would say the graph has been reflected in the x-axis and it has been dilated by a factor of 2 from the x-axis. So let's have a look now at what occurs if we change the value of b, that is the number inside the brackets. So for this example, I've chosen to have x minus 3 inside the brackets, that is my b value is positive 3. Now make sure that you don't get confused and write down that b is equal to negative 3 because the formula above says x minus b. Now in order for you to get x minus 3, the b value must actually be positive 3 because x minus positive 3 will get you x minus 3 inside the brackets. And of course, with our c value being 0 and our a value being 1, that'll simplify to get us x minus 3 in brackets squared. Now if you have a look at what occurs here, the graph actually moves to the right 3 units. That is, the turning point that was at 0, 0 now moves to the coordinates 3, 0. And we say that in this case, the graph has been translated 3 units to the right. Having a look at a new example now, you can see that in this case my b value is actually equal to negative 2 because when you have x minus negative 2 you get x plus 2 in brackets squared. Now because my b value is equal to negative 2, my graph actually shifts 2 units to the left. That is, it gives us a new turning point at the coordinates negative 2, 0. And in this case, when we're asked to comment on any transformations that have occurred, we would say that the graph has been translated 2 units to the left. So summing up, the b value essentially just moves the graph left or right. And it's also extremely important to remember that the b value actually moves the graph in the opposite direction to what you might initially think. That is, if it says x plus 2 in brackets squared, it doesn't move it in the positive direction. What it actually does is it moves it in the negative direction. And if it says x minus 3 in brackets squared, it doesn't move it in the negative direction, it actually moves it in the positive direction. Having a look at the effect of the c value now, what we'll do is we'll make our c value equal to 10. Our b will be equal to 0 and our a will be equal to 1. That will simplify to get us y equals x squared plus 10. Now what you can see here is each of our dots is actually moving up 10 units because after we've gone through and squared each number to get us the graph of y equals x squared, we just add 10 to the y value in order to find out how high up it is. Also noteworthy is that the coordinates of the new turning point is at 0, 10 because the graph has moved 10 units upwards. And in this case we say that the graph has been translated 10 units upwards. Now what do you reckon will happen if our c value is negative? Well, let's check it out. That is, I'm going to make my c value equal to negative 15. So what you can see here when it simplifies is you get y is equal to x squared minus 15. And as you can see, all of my dots are now moving down 15 units. And because of this, the coordinates of my new turning point will be at 0, negative 15 because my graph has moved 15 units downwards. Or in other words, we say that the graph has been translated down 15 units. So in summing up, what the c value does is it moves the graph up or down. It will also actually be the y coordinate of the turning point. Alright, so now it's time to put it all together and see what we get. So in this case I've made my a value 2, my b value 1 and my c value negative 8. Now when you're asked to sketch the graphs of quadratic functions in turning point form, the best thing you can do is find a starting point, and what we do is we usually use a turning point for this. Now because we know the graph has been moved 1 unit to the right and 8 units down, we know that the turning point is actually at the coordinates 1, negative 8. And now that we know our turning point, we need to find our y-intercept. Now of course to do that, what we do is we make x equal to 0. So what you can see here is I've written out the equation of the line, and substituting x equals 0 now, you get y equals 2 bracket 0 minus 1 squared minus 8. Now 0 minus 1 is negative 1, and when I go through and I square negative 1, I get 1. So 2 times 1 is 2, and 2 minus 8 is negative 6, so I get the coordinates 0, negative 6. Now as you can see, I've written the coordinates of my y-intercept right next to my working out, so that it's a point of reference to come back to later. And of course the next step is to go through and plot this point on the axis, as you can see here. It's now time to find my x-intercept, so to do that I make my y equal to 0, but before I do that, what I'll do is I'll go through and write out the equation of my line once again. Then when I make it equal to 0, you'll get 0 equals 2 bracket x minus 1 squared minus 8. Add 8 to both sides gets us 8 is equal to 2 bracket x minus 1 squared. When you divide both sides by 2, you get 4 is equal to x minus 1 squared. Square rooting both sides now, you'll get plus or minus 2 is equal to x minus 1, and then adding 1 to both sides will get us 1 plus or minus 2 is equal to x. So therefore 1 plus 2 is equal to 3, and 1 minus 2 is equal to negative 1. This of course gives us the x coordinates of 3, 0 or negative 1, 0. And as you can see, I've written them once again as a point of reference right next to my working out, and I'll go through and plot them on the graph as you can see here. And of course, once I've got all of my points of interest plotted, all I need to do is go through and join these dots with a line, as you can see here. And so when you're asked what kind of transformations have occurred to the graph of y equals x squared, we can say that it's been dilated by a factor of 2 from the x-axis, it's been translated 1 unit to the right, and it's been translated 8 units down. And as you can see, all of these dots now fall on our new line.
Cool. Alright guys, let's finish off this little introduction now with a little step-by-step explanation of how to work with quadratic functions in PowerForm. Let's check it out.
So as you've just seen, today we're learning all about how to sketch the quadratic functions using the turning point method. Now there's a few things, guys, that you need to know in order to be able to do this well. And the first one being is the general rule for this method, and that is y is equal to a bracket x minus b squared plus c that you can see here. Now our a, our b and our c values that you've seen before in the animation are going to all affect the graph in a different way. For example, our a value that you can see out the front here, that's going to affect the dilation factor. Now the dilation factor is basically the stretch from the x-axis. Alright, now the a value, if it's greater than 1, the graph becomes thinner. So let's have a look at the graphs down here. I've got my a value of 1 here. If my a value is greater than 1, the graph becomes thinner. You can see it like you can see in the red one here. Now that might be an example, might be y is equal to 2x squared, for example. Now if our a value is between 0 and 1, our graph gets wider, like you can see here. For example, this might be y is equal to 1/2 x squared, because you can see that our a value is between 0 and 1, and the graph gets wider there. And of course, if our a value is less than 0, the graph reflects in the x-axis. So what that does is you imagine there's a mirror going along here, and then our negative a value means that the graph flips over and goes in the other direction, making it a maximum turning point rather than a minimum turning point. Now for our b value, what that does is it basically affects our horizontal translation, that is, it moves the graph left or right. So for x plus b, the graph is translated b units to the left, that is, in this direction. So if it's plus b, it goes sort of in the opposite direction to what you would imagine. Where if it's x minus b, the graph translates b units to the right. So once again, it goes in the opposite direction to what you'd imagine. So the b also is the x coordinate of the turning point. Right, really important that we recognise that. Now our c value, well, that is our vertical translation up or down. So when the general rule has plus c, the graph will be translated c units up. And if the equation says minus c, so minus 3 for example, the graph will be translated c units down. So this is pretty much what you'd imagine based on the plus or minus. Now there's a few other things that we need to take into consideration when sketching the graphs of quadratic functions using the turning point method. The first being, is the function in turning point form already? That is, y equals ax minus b squared plus c. Or is it in the original form where you've got ax squared plus bx plus c? Now if it's already in the turning point form, then you don't need to worry. But if it's in your y equals ax squared plus bx plus c that you can see here, what you need to do is you need to go through and complete the square in order to be able to convert it into turning point form to make your life easier. Now the second step is to locate the coordinates of the turning point. So for the function y equals a bracket x minus b squared plus c, your turning point you can get from your b value here and your c value here. Now remember, your b you actually think the opposite. So if it said x plus 3, then you would write negative 3 here because it's the opposite of what you think. And your c value, well, that's just as it says. So if it says plus 2, then you would write just 2 there. Now if it said x minus b, well then it's going to be positive b there. Now your third step is to locate your y-intercepts by making x equal to 0 and then solving. Then of course you've got to find your x-intercepts by making y equal to 0 and solving. And then once you've got your turning points and your x and y-intercepts, you can then plot these points and sketch the graph.